In the previous video we installed a Tesla Model S electric motor on the boat. And now it's time for the battery. That is not as straightforward as a normal 24 volts battery or even as an electric car battery. Especially fire safety is more important, since we cannot just step off if a battery catches fire in the middle of the ocean. My name is Gijs and this is my dad. This is Schoener Tijgerhaai. 3 years ago we started a major rebuild to get her ready for new adventures. And we're sharing the process with you. Subscribe to stay tuned. As many of you have pointed out after the last video, lithium batteries are not something to be taken lightly, especially on a boat. We did install a 24 volts drop-in house battery a couple months ago, lithium iron phosphate, with 8 kWh of energy and an internal battery management system. Basically, all in one box, plug and play, very safe. That is not how it works with a battery that is meant to power an electric car motor. For starters, an EV motor does not run on 24 volts, but in a voltage range of 3 to 400 volts direct current. And some newer models even go up to 800 volts. But ours is in that first group. What does that mean? Well, touching a live 400 volts DC wire can definitely stop your heart. And the higher the voltage, the further electricity can jump through air. So everything in the system has to be designed and approved for that voltage. Does that make it complicated? Not really. You just have to buy the right stuff. We also have 3-phase 400 volts alternating current on board, and for that you also need the right stuff. But DC and AC each need different stuff. Running on 3 to 400 volts DC means we cannot use standard Victron or any other brand drop-in LFP batteries. Theoretically, we could string 15 of them together and you would also have the right voltage, but electrically that does not make it a safe battery. For example, a Victron battery management system does not support a system voltage higher than 70 volts. That means if we exceed that, there is no safety approval and certification, monitoring and charging is going to be a problem, and it's unknown how the system will behave on the whole. We're also not going to build our own lithium batteries. First, because of safety approvals and certifications, and second, because we simply cannot build anything that comes close to the safety testing and proven reliability of a proper A-brand battery manufacturer. That puts us in the world of EV batteries, with EV-grade battery management systems, which makes sense for powering an EV electric motor. LFP batteries in electric cars have really taken off in the last couple of years. 45 to 50% of all new EVs now have an LFP battery pack. But almost all of those have been produced in China, and because the large-scale production is still relatively new, almost none of those packs end up in the consumer market. So for now, we have to go with standard EV batteries, using NMC chemistry, which has been around for more than a decade and there's a huge consumer aftermarket. The Tesla that our electric motor came out of probably also used an NMC pack, but the risk with a used battery is that you do not know what it's been through. Instead, we can buy new certified modules of a reputable brand. Don't get me wrong, we would prefer an LFP battery, but it is simply not available for us right now. NMC batteries come with a bigger risk of thermal runaway than LFP. Thermal runaway occurs when something inside a battery cell gets damaged or stressed enough that it starts heating itself faster than it can cool down. Once that happens, the temperature rises uncontrollably, the materials break down, oxygen is released inside the cell, and the cell basically becomes its own fuel source. This can be caused by 4 triggers. Mechanical damage, which includes crushing or puncture, electrical abuse, like overcharging, over-discharging or high current spikes, thermal abuse, like fire near the battery or a neighboring cell in runaway, and manufacturing defects, which can create an internal shortcut. The thing with thermal runaways is you cannot fight them. You cannot stop a thermal runaway inside a cell that has already started. You can cool the surroundings, but you cannot stop the chemical reaction inside that cell. The good news is that modern EV cells are extremely well made. The industry has had more than 15 years to improve manufacturing, and spontaneous runaways are very rare. But we're not gambling the whole ship and our lives on those odds. We're gonna have to be prepared to deal with it. And in several ways, because one safeguard is no safeguard. So our strategy has 3 layers. First, minimize the chance of a thermal runaway. With a proper BMS, a watertight enclosure, proper charging and a proper installation. Second, if a cell fails anyway, contain it to that one battery module. And third, if containment fails, cool the entire pack by flooding it with fresh water. This sacrifices the battery, but it prevents the heat from spreading to the rest of the ship. The goal is simple: let the affected cells burn themselves out without taking the vessel with them. The first safety barrier is a proper electrical and electronic system. We are centralizing all of that, the brains of the battery, in one high voltage DC cabinet. Inside, there is a non-conductive backplate where all components mount cleanly. Just a quick disclaimer, this whole high voltage system wasn't something that we invented ourselves. The overall design, the component selection and the BMS configuration were all done by EV Europe, who are real experts in this field. They supplied the battery modules and the high voltage architecture, and we're building the system using their designs. First, the BMS. This is the actual brains of the battery. It receives data from all the cell sensors, temperature probes, current sensors, insulation monitor and the safety interlock switches, and it controls the contactors, the chargers, the alarms, everything. Then we have the 2 main high voltage contactors, one in the positive line and one in the negative line. The BMS decides if they're allowed to close, and it opens them immediately if anything is outside of safe limits. Next to that is a smaller high voltage contactor, controlling the pre-charge. When the BMS gives green light, this one closes first, feeding the entire system through this resistor, this big flat thing. So the capacitors inside the motor controller and the chargers can slowly rise to pack voltage. Without pre-charge, closing the main positive contactor would cause a huge inrush current as the whole system jumps to 400 volts in a split second, which is very bad for everything downstream. Down the positive line we have 3 fuses, one for the Tesla drive unit, one for the 3-phase charger and one for the single-phase charger. The only fuse that is not in this cabinet is the main pack fuse. That one lives inside the battery enclosure, which we'll get to later. In the negative line, after the main contactor, we have the current sensor, which talks directly to the BMS, so it knows exactly what the pack is doing. Right after that, we have a central negative bus bar where the line splits towards the 3 downstream components. Another safety item is the insulation monitoring device. It's connected to the ship's hull, and instead of measuring the voltage differences, it injects a tiny signal, basically a coded pulse, into both the high voltage positive and the high voltage negative. If that signal comes back through the hull, there's an earth fault, and the IMD immediately tells the BMS to open the main contactors. There's also a small buzzer inside the cabinet, directly controlled by the BMS, and a larger relay that drives a big alarm buzzer in the wheelhouse. With all the wiring installed, it looks something like this, and cleaned up like this. All cables are clearly identifiable by color, matching the electrical drawings. You might wonder if all these open, unprotected terminals are dangerous. They are. But there's a safety interlock switch in the door. If the door opens, the interlock loop breaks, the BMS drops the contactors and the whole system goes dead. The only 2 lines that remain live are the main positive and negative feeding the contactors themselves. So those get protective covers to prevent accidental touching. On the outside of the door there's an emergency stop switch. It does the same thing as the door interlock, but it's also wired directly into the control line of the contactors. So even if the BMS were to fail, the emergency stop will always open the contactors. And finally, there's a display on the door, so we can monitor everything without opening the cabinet. And the BMS also feeds data to our navigational displays, so we can keep an eye on the battery from the wheelhouse, and even from the aft deck. But a proper high voltage and battery management system is only one part of minimizing the risk of thermal runaway. We also need an enclosure for the batteries. We have a used but still good stainless steel water tank laying around, and we can turn that into a battery box. That box can contain and help us fight any possible battery fire. The box has to be watertight to keep salt water out and fresh water in if we ever need to flood the battery pack to cool it down. To help keeping the box watertight, it gets a minimum number of penetrations. 2 for the high voltage cables and 1 for the battery management system communication cable. On the other side we need a fresh water inlet and a drain. And of course, a battery fire inside a sealed box means overpressure and toxic gases, especially once you start adding water. So we need a ventilation pipe that channels hot gases to the outside of the ship. But then if we leave that open, it compromises our water and air tightness. So we're installing a rupture membrane in the ventilation pipe that is able to stay closed during normal use air expansion, but in case of overpressure due to fire and water evaporating, it will break. So we need a rupture pressure of around 0.2 of a bar. Calculations on when a sheet of metal ruptures are a bit vague, and there's loads of variables in them. So instead of calculations, we rigged up this pressure testing contraption to do some real world testing. We had some brass sheet laying around of 0.2 mm thick, so we decided to give that a go. That was way too strong. At 1.5 bar it still didn't break. So I tried some aluminum foil instead. I did a couple of tests and every time the membrane popped at around 0.2 to 0.3 bar. So that is perfect. It's stronger than fluctuations in air pressure due to heat or weather, but it breaks way before the lid of the box starts ballooning. To make room for the battery box, we're removing one of the 2 diesel generators. We're not using this smaller one anymore anyway. We still have the big generator, so this space is perfect for the battery system and the large inverter. With that out of the way, as always, fresh paint. And now we can install the new high voltage cabinet, the 3-phase charger inverter and the single-phase charger. Both chargers are programmed with a safety margin on the batteries. We're never charging them all the way to 100%, but more like 85 to 90%. And the inverter won't pull them lower than about 10 to 15%. That means the cells are never stressed to the extremes, which reduces the chance of failures and significantly increases the lifetime of the batteries. It is important to mention that these are not fast chargers. The big one is 20 kilowatts, which can charge the whole pack in just over 3 hours, but that is nothing compared to fast chargers for electric cars along the highway, where going from 10 to 80% typically takes around half an hour. This charger also inverts up to 20 kilowatts of battery power to 3-phase AC power, which means our 15 kilowatt bow thruster can run directly from it. And we don't need to start a separate generator anymore during maneuvering. Now we can install the battery box and the batteries themselves. These batteries are made by the Korean company SK Innovation for the Mercedes-Benz supply chain. So they are top-tier automotive batteries. But they never went into a vehicle. They are unused modules that EV Europe acquires through their normal supply channels. The modules themselves are built in a sealed aluminum casing, but they don't carry an official IP rating as standalone units. That's one of the reasons they sit inside our dedicated battery box, where all the high voltage cables and connectors are protected in a controlled environment. Together they give us about 64 kilowatt hours of usable energy. That is not a huge amount for a vessel of this size, but it's more than enough for what we actually need. Maneuvering in and out of harbors, raising the sails and running the boat quietly at low power. And the real point isn't the capacity, it is that the Tesla motor can regenerate while we're sailing. That energy goes straight into the battery and through the inverter it becomes 3-phase AC power for everything on board. They have extensive internal temperature monitoring, which you can see from the sheer number of small wires running from the modules to the battery group modules, sending all that data to the BMS. That level of monitoring is key for early fault detection inside the batteries. We didn't have enough material for the lid, so we had to order a new plate for that. To make sure it seals watertight, it gets screwed down with dogs that we still had laying around. And we're using high temperature silicone foam as a gasket. We have almost spent this entire video on our first line of defense, making thermal runaway unlikely in the first place. But we still have layer 2 and 3, which come into place when something actually goes wrong inside the cells. The second line of defense is containing a starting runaway to that one module. We have 4 modules in total, and losing one of them is of course far better than losing all 4. The BMS helps here as well. It keeps monitoring the temperatures and will shut down charging and discharging if a runaway is detected. But it cannot stop a runaway once it has started inside a cell. So it's important to quickly go through the stages of thermal runaway inside a battery like ours. When a thermal runaway is triggered, the first thing that happens inside a cell is the protective layer on the graphite anode starts to break down. Inside that cell, the temperature rises to around 80 to 120 degrees Celsius. This is not a very fast process. It can take up to tens of minutes. And in this stage the BMS already detects that something is wrong and it will open the high voltage contactors. But the module itself doesn't heat up much yet. The second stage is gassing or venting. At a cell temperature of around 120 to 180 degrees, the electrolyte starts to boil. Pressure rises and now the temperature of the module casing starts to increase. The temperature in our battery box rises with it, typically up to around 80 degrees. This stage can take tens of seconds to minutes. And this is already where our first fire containment system activates. We're installing a FirePro aerosol canister that triggers at 79 degrees Celsius. And it fills the entire battery box with a potassium-based aerosol. That aerosol absorbs heat and it disables the reactive oxygen and hydrogen particles that are needed to sustain a flame. With a bit of luck, this already stops the spread of heat to the next cell, and it lets the one affected cell burn itself out in a controlled way. The third stage is the exothermic breakdown of the cathode. Inside the cell, the temperature now shoots past 180 degrees and the chemistry becomes self-heating. This part goes much faster, usually seconds, and the module casing starts to heat up more noticeably. But even here, the temperature inside the cell is far higher than what you would see on the outside of the module or inside the battery box. The fourth stage is the actual thermal runaway event, the short jet flame. Inside the cell, temperature can reach several hundred degrees and the cell vents a hot burning jet for 1 to 5 seconds. This is the dramatic part you see in online videos. But it's important to understand that it only happens after all the earlier stages. First heating, then gas, then pressure, and only then the jet flame. And because the FirePro has already filled the enclosure with aerosol, flames cannot form outside of the module. So even during this stage, the heat stays contained inside the battery box. And that brings us to our third line of defense. On the outside of the battery box lid we have a temperature sensor. It's mounted on the outside because we don't want extra cable penetrations into the box and because it must keep working even if the box fills with water. When the lid reaches around 100 degrees Celsius, that sensor starts a separate water pump, sucking water directly from our freshwater bunkers. We have 7 tons capacity and we keep them topped up most of the time, so it won't leave us thirsty. Inside the box there's a sprinkler head that only pops at 141 degrees Celsius, to give the aerosol the chance to do its job. But if the temperature does continue to rise, the sprinkler head will activate and the pump will start filling the box with water. At the same moment, the brake plate in the overpressure exhaust pipe also ruptures, so any toxic gases are automatically vented to the outside of the ship. That means we won't have toxic gases in the engine room or anywhere else in the accommodation. The switch on the lid turns the pump off again when the temperature drops below 80 degrees. And it switches back on at 100 degrees if the temperature rises again. That way we prevent the pump from overflowing the box. And we can safely continue our journey using the diesel engine, the diesel generator and the smaller 24 volts battery and inverter. And as you may have noticed, none of this requires human intervention. We might be sleeping or not even on the boat when something goes wrong. The BMS is the first automatic protection, the aerosol is the second and the flooding system is the third. We could have the BMS control the total flooding pump as well, with all the temperature sensors that it has inside the batteries. But we still want it to work even if all our sensors are cooked, so we kept it simple. And if we come back to the ship in the morning and we see that all our batteries are flooded, we will probably say a couple of bad words, but the ship is saved and so are we. And that is how you can safely install lithium EV batteries on a boat. I'm not saying this is the way, but it's a way. We still have to do a big part of the wiring before we can actually switch the batteries on. And after that, we still have to program the Tesla VCU before we can do our first small battery-powered test cruise. But this is all for now. If you have any questions or remarks, please let us know in the comments. Thank you for watching and I'll see you next time.